Hello, and thank you for being here. Tonight, we will slowly drift into a state of calmness and explore the long, quiet evolution of artificial intelligence, a story that begins not with flashing screens, but with simple questions whispered in the minds of mathematicians and dreamers. Imagine rooms filled with softly humming machines, early mechanical ideas inspired by ancient myths of artificial beings, and pages of logic where numbers learn to represent thought. As time moves forward, we pass through moments of patience and uncertainty, from early calculating engines to machines that began to recognize patterns, adapt, and quietly learn from the world around them. This is a journey shaped by curiosity, pauses of doubt, and sudden breakthroughs, where human imagination and silicon circuits slowly grew side by side. If you enjoy these relaxing moments, please consider leaving a like, subscribing, or sharing your thoughts below. You can also turn on the notification so you don't miss any of our future journeys together. But for now, just breathe. Let your body relax. Release any tension and allow your mind to drift. Let's begin. Long before the first hum of an electric current, long before circuits would ever awaken under human touch, the idea of intelligence beyond flesh and blood stirred in the imagination of humankind. In the soft glow of oil lamps, scholars, artisans, and storytellers pondered the possibility of life fashioned from gears, clay, or carved wood. Ancient Greece offered the earliest whispers of such wonder, in tales of animated statues that moved on their own, figures imbued with purpose by the gods or by clever ingenuity. Hephaestus, the divine blacksmith, forged golden attendants, mechanical beings that served without fatigue or complaint, and the stories lingered as more than myth. They were explorations of a question that would echo across millennia. Could the essence of thought exist outside the human mind? These early visions were not mechanical blueprints in the modern sense. They were poetry and philosophy, gestures of curiosity cast in stories. Philosophers asked whether reasoning itself was a property confined to living creatures, or whether it could, in theory, be mirrored in material forms. Plato's dialogues hinted at distinctions between body and soul, between what acts and what perceives, laying conceptual stones that would underpin centuries of inquiry. In the flickering candlelight of ancient libraries, scribes traced diagrams of moving mechanisms, water clocks, and early automata. Each figure, each turning wheel or flowing stream embodied a fascination not with conquest, but with comprehension. The desire to see intelligence as a pattern, something observable, something that might one day be replicated in the world of human craft. By the medieval period, the imagination of mechanical life had grown more tangible. In workshops tucked beneath stone roofs, artisans created automata that moved in eerily lifelike ways. Knights in shining armor would march across tabletops, trumpeters would lift their instruments and produce sound, and dolls would nod, wave, or write. Driven by the intricate interplay of gears, weights, and water, these creations were marvels of observation, mimicry, and ingenuity. There was no intention of replacing human thought, only the pursuit of fascination, the exploration of boundaries between animate and inanimate. Visitors would watch in hushed awe as the clockwork servants of princes and scholars performed their rehearsed gestures, a silent testimony to human curiosity and technical skill. In the East, similar reveries emerged. Chinese and Islamic engineers devised elaborate water-driven figures, musical machines, and automata that danced or poured tea. Across continents, the drive to recreate life's motions reflected a universal contemplation. Intelligence, perception, and behavior could perhaps be understood, modeled, and honored through physical form. There was a serene humility in this pursuit. The machines were not rivals to humanity, but mirrors, reflecting the structure, rhythm, and logic that humans recognized within themselves. Even in the shadows of these mechanical wonders, literature and myth continued to probe subtler questions. The golem of Jewish legend, fashioned from clay and brought to life by ritual and intention, embodied both potential and caution. Here was a being animated, yet dependent upon the wisdom and care of its creator. The stories were reminders that intelligence, whether divine, human, or mechanical, was never free from responsibility, never divorced from context. In these tales, one senses the emotional undertone that would follow AI for centuries. Curiosity intertwined with reflection, wonder mingled with caution, imagination tempered by philosophy. This era also witnessed the rise of intricate diagrams and textual reflections, technical manuscripts that traced not only gears, but ideas. Leonardo da Vinci sketched self-propelled carts and mechanical knights, experiments in motion that, while rudimentary, carried the spirit of exploration. Scholars contemplated pneumatics, hydraulics, and levers, with the same reverence that poets reserved for stars or oceans. Each turning gear was a meditation, a silent question cast in motion. Can the essence of thought, of purpose, be contained in the physical? And if so, what does that reveal about the human mind itself? Through these centuries, the notion of artificial intelligence remained unthreatening, almost intimate. It was never an instrument of domination, never a harbinger of conflict, but rather a reflection of human curiosity. In workshops, dimly lit chambers, and scholarly halls, people measured, sketched, and experimented. They sought patterns, causes, and rhythms. In doing so, they laid the emotional and conceptual foundations that would later allow society to imagine thinking machines in entirely new ways. The mechanical figures, animated statues, and philosophical questions of ancient civilizations were the seeds of a broader understanding. Intelligence could be approached, studied, and perhaps, in time, replicated. Even as night deepened across medieval cities, one could almost imagine the faint movements of clockwork figures, the gentle ticking of intricate mechanisms resonating against stone walls, a chorus of miniature life echoing humanity's own. These subtle vibrations were meditations on the possibility of mind without flesh, cognition without consciousness, purpose without soul. They were invitations to explore, to dream, to understand. The longing for artificial intelligence was never simply a technical pursuit. It was a philosophical journey, an emotional inquiry. The early stories, diagrams, and automata connected deeply to questions about what it meant to be alive, to reason, and to create. They whispered that intelligence might someday be more than human, yet they grounded it firmly in human observation, human ingenuity, and human imagination. There was a calmness to this exploration, a measured patience, as if the very act of imagining intelligent machines was itself a way of contemplating humanity. Looking back through the flickering centuries, the line from Hephaestus's golden servants to medieval automata, from the golem to Leonardo's sketches, becomes a subtle thread weaving through human thought. It is a continuity, linking philosophy, artistry, and curiosity. These early musings remind us that the history of artificial intelligence began not with electricity, not with binary code, not with silicon and processors, but with contemplation, observation, and the tender act of wondering what it means to think. As candlelight dances over old manuscripts and the soft whisper of turning pages fills silent chambers, one can trace the beginnings of AI as a story of patience and reflection. Each myth, each automaton, each diagram speaks of a careful exploration, an openness to possibilities unimagined. And while no machine of that era could truly think, the foundation for understanding intelligence, for questioning the boundaries of life and mechanism, had been laid. In this dim, reflective world of gears, stories, and imagination, one senses the continuity of human longing. The questions asked by philosophers and artisans of centuries past still resonate. Can a creation mirror thought? Can the mind be modeled? Can intelligence exist in forms other than our own? These are not urgent queries, nor are they fears. They are meditations, patient and deliberate, stretching forward across time. They lead directly to the next chapter, where the slow, careful formalization of logic and mathematics begins to bridge the chasm from philosophical wonder to computational possibility. The legacy of these early dreams of thinking machines endures not in practical devices, but in the reflective human spirit. It is the patient curiosity, the willingness to explore unseen mechanisms, the fascination with the potential of mind that links the flickering candles of ancient chambers to the glowing screens and humming processors of today. And so, the story of artificial intelligence begins in human imagination, in myth and craftsmanship, in the subtle, persistent whisper that asks, what is thought, and how might it one day be embodied beyond ourselves? Centuries after the first automata clanked and moved in workshops and courts, the focus of human curiosity gradually shifted from physical mimicry to the abstract structure of thought itself. Across study halls and candlelit libraries, thinkers began to explore the rules underlying reasoning, seeking patterns in argument, deduction, and inference. Logic, the disciplined language of valid thought, emerged as a bridge between imagination and mechanism, offering a way to capture reasoning in formal structures that could one day guide machines. Aristotle, in the 4th century BCE, laid the foundation with his syllogisms, mapping patterns of deduction that allowed conclusions to flow inevitably from premises. In these early investigations, thought was no longer ephemeral or mystical. It could be observed, categorized, and, crucially, systematized. The medieval period nurtured this fascination, though often quietly and indirectly. Scholarly monasteries and the early universities of Europe preserved and expanded upon classical works, translating and commenting on texts from Greek and Arabic sources. Scholars engaged with abstract reasoning, probing distinctions between necessity and possibility, cause and effect, and the rules governing valid inference. Within these careful studies, one sees the first conceptual framework for computation. The recognition that ideas, like numbers, could be manipulated according to formal laws. Logic was no longer only a philosophical exercise. It became a scaffolding for the precise handling of symbols, a language that could, in theory, be followed mechanically. The 17th century brought a striking turn. Gottfried Wilhelm Leibniz imagined a universal language of reasoning, a symbolic system in which disputes could be resolved through calculation rather than argument. His vision of a characteristica universalis and a calculus ratiocinator suggested that reasoning could be reduced to symbolic manipulation, a notion both radical and extraordinarily prescient. Leibniz's work anticipated the notion that machines might one day process thought, not through inspiration, but through structured, formal steps. He envisioned devices capable of performing these symbolic calculations, mechanical aids to intellect, extending the capabilities of human reasoning into material form. By the 19th century, symbolic logic and mathematics began to converge in ways that laid the groundwork for computational thinking. George Boole, in particular, transformed reasoning into an algebraic system, encoding logical statements as symbols capable of manipulation through defined operations. In Boole's formalism, propositions could be represented with ones and zeros, truth values that obeyed strict algebraic rules. This elegant reduction of abstract thought to symbolic computation set the stage for electronic computation centuries later. Boole's work demonstrated that reasoning could be quantified, that rules of logic could become manipulable, and that machines, conceivably, could perform tasks that required judgment, provided they followed precise rules. Simultaneously, mathematicians such as Charles Babbage and Ada Lovelace began translating these abstract concepts into mechanical possibility. Babbage's difference and analytical engines were not merely calculating machines. They were conceptual experiments in automating symbolic reasoning. Lovelace, contemplating the analytical engine, recognized that machines could go beyond number crunching to execute any set of operations defined in symbolic terms. Her reflections were profound. She foresaw that machines could follow sequences of instructions in ways that resembled, in certain respects, thinking, albeit bound by explicit design. These ideas represent a careful meditation on the nature of intelligence, a bridge between philosophical speculation and engineered process. Logic also found a home in probability and early combinatorial reasoning. Mathematicians explored ways to formalize uncertainty, laying subtle groundwork for methods that would only flourish much later in data-driven approaches. Every theorem, every symbolic transformation, and every diagrammatic proof added to the accumulation of tools that would allow human thought to be mirrored, in part, by machines. The progression from Aristotle's syllogisms to Boole's algebra was neither sudden nor dramatic. It was deliberate, cumulative, and reflective, a centuries-long meditation on the essence of reasoning. By the early 20th century, these foundations crystallized in forms that directly informed what would become computer science. Bertrand Russell and Alfred North Whitehead's Principia Mathematica sought to formalize all mathematics through logic, a vast and patient exercise in symbolic structure. Kurt Gödel later revealed both the power and limits of formal systems, showing that no finite set of rules could ever capture all truths, a humbling reminder of the subtlety of thought. These insights shaped the conceptual environment into which Alan Turing would introduce his revolutionary questions. If logic could be formalized, could machines be constructed to follow it? Across these developments, a subtle pattern emerges. Human ingenuity repeatedly sought to map thought itself. Logic, symbolic representation, and algebraic formalism allowed abstract reasoning to become manipulable, analyzable, and ultimately mechanizable. Mathematics became more than a tool for counting or measurement. It became a language for thought, a medium in which the very structure of intelligence could be encoded. By the time mechanical and later electronic computation emerged, Centuries of reflective reasoning had laid the cognitive and conceptual groundwork. From ancient syllogisms to formal symbolic systems, the history of computational thought is not merely a history of numbers, but a history of abstraction, careful reflection, and incremental insight. It is a story of patient humans seeking to understand the architecture of thought, translating intuition into structure and curiosity into method. Logic and mathematics offered not immediate machines, but the promise that thought could be expressed, tested, and eventually enacted in forms beyond the human mind. In these sequences of symbols, diagrams, and proofs, one senses the persistent human desire to extend intelligence, to explore not only the limits of knowledge, but the possibility of recreating cognition itself. Each theorem, calculation, and logical formulation is a meditation on the nature of mind, preparing the way for machines that could, in time, move from imitation to true computation. In this continuum, the mind of the human thinker and the emerging idea of artificial intelligence are inseparably intertwined, an enduring reflection of humanity's quest to understand itself through reason, structure, and the subtle elegance of abstract form. In the midst of the 20th century, a revolution in thought began to take shape, one that would transform speculation about machines into a rigorous field of inquiry. Alan Turing, a British mathematician and logician, approached the question of intelligence with a clarity and precision that bridged philosophy, mathematics, and nascent computing. In rooms filled with the muted hum of early electronic machines and the scratch of pen on paper, he asked a deceptively simple question: could a machine think? Unlike earlier dreams of mechanical life, Turing's inquiry was framed not in myth or metaphor, but in terms of observable processes, testable behaviors, and formal reasoning. During the Second World War, Turing's brilliance found urgent application in cryptography. At Bletchley Park, the mathematician helped develop machines capable of deciphering the encrypted messages of the German Enigma, an achievement that demanded both creative intuition and rigorous logic. These early computational devices were designed for a single monumental purpose: pattern recognition and algorithmic processing at scales impossible for humans. The environment was intense, filled with flickering relays, mechanical clatter, and the intensity of minds focused on unraveling complexity. Yet beneath the immediate task, Turing was simultaneously exploring the deeper nature of computation itself, asking whether processes governed by strict rules could emulate aspects of human reasoning. It was during this period that Turing formulated the concept of a universal machine, now known as the Turing machine. Unlike any physical device, the Turing machine was a theoretical construct, capable of reading, writing, and manipulating symbols on an abstract tape according to precise rules. In its simplicity lay extraordinary power. Any computation that could be described algorithmically could, in principle, be performed by such a machine. Turing's insight redefined the boundaries of mechanical thought, demonstrating that the formal manipulation of symbols could stand as the foundation for intelligence, at least in operational terms. After the war, Turing continued to explore the implications of his ideas in quieter academic settings. It was then that he proposed what would become known as the Turing test, an experiment not in mechanics, but in behavior. He suggested that a machine could be considered intelligent if it could produce responses indistinguishable from those of a human interlocutor. This reframing shifted the discourse from the inaccessible question of internal consciousness to observable interaction, emphasizing performance over speculation. In doing so, Turing established a pragmatic benchmark for machine intelligence, one that could guide future research while remaining grounded in measurable outcomes. Turing's work built directly upon centuries of abstract reasoning. The symbolic logic of Boole, the structured proofs of Russell and Whitehead, and the combinatorial insights of earlier mathematicians were all integrated into his vision. His genius was to see that these abstract structures could be embodied in a machine capable of execution, and that thought could, in principle, be modeled as a sequence of rule-governed operations. The interplay of theory and potential implementation gave Turing's ideas a rare duality. They were simultaneously philosophical, questioning the nature of intelligence, and practical, laying the groundwork for computational devices. The era following Turing's theoretical contributions witnessed the first experiments with electronic computing machines that could realize aspects of his vision. Early computers like the Manchester Mark I and the ENIAC did not think in any meaningful human sense, but they demonstrated that mechanical processes could manipulate symbols, perform arithmetic, and execute sequences of operations with unprecedented speed and accuracy. These machines echoed Turing's abstractions, bridging the divide between mathematical reasoning and practical computation. In doing so, they also highlighted the distinction between raw calculation and intelligence, a subtlety Turing himself emphasized. The ability to process symbols does not, by itself, constitute understanding, but it opens the door to systematic exploration of cognitive tasks. Turing also anticipated many questions that continue to shape artificial intelligence today. He recognized limitations, noting that some problems cannot be solved by purely mechanical means, an early insight into computational complexity and undecidability. He reflected on the potential for machine learning, hypothesizing that machines could be trained through experience, a precursor to ideas that would emerge decades later in data-driven AI. His writing balanced optimism with caution, revealing both the promise of intelligent machinery and the careful attention required to understand its capabilities and boundaries. The intellectual atmosphere of Turing's time was one of exploration tempered by rigor. His correspondence with contemporaries, his notes on early computers, and his contemplations on machine learning illustrate a mind deeply engaged with both abstraction and implementation. Each theorem, each theoretical device, each hypothetical test was part of a continuum extending from ancient philosophical inquiries to modern electronic computation. Turing's work serves as a central bridge in the story of artificial intelligence, connecting the symbolic logic of centuries past to the electronic and algorithmic breakthroughs that would follow. By examining Turing's contributions, one appreciates that artificial intelligence did not emerge suddenly with hardware or code. It was seeded by decades of careful, reflective thinking about reasoning, formal systems, and the nature of intelligence itself. The brilliance of his theoretical machines, the subtlety of the Turing test, and the practical implications for computation collectively reframed the possibilities for human ingenuity. Turing's legacy endures not only in the devices and algorithms that followed, but in the enduring question he posed: what does it truly mean for a machine to think? Through this lens, we can trace a seamless thread from abstract reasoning to practical computation, from symbolic logic to programmable machines. Turing's work reminds us that intelligence, whether human or artificial, is ultimately a matter of pattern, process, and the careful orchestration of rules. In reflecting on his contributions, one observes the patient unfolding of centuries of thought, the gradual accumulation of ideas, and the persistence of curiosity that allows humans to envision minds beyond themselves. It is here, in these mid-century reflections, that the foundation for modern artificial intelligence solidifies, connecting philosophical inquiry with tangible computational possibility. In the years following Alan Turing's theoretical breakthroughs, the abstract vision of computation began to take tangible form. Enormous machines, often filling entire rooms, emerged from the laboratories of universities and early technology companies. These computers were unlike any device that had come before. Vast arrays of vacuum tubes, switches, and punched cards worked in unison to execute sequences of instructions with precision and consistency. They lacked intelligence in any human sense, yet they embodied the principles Turing had described, performing calculations and processing symbols on a scale previously unimaginable. The early 1950s marked the rise of symbolic artificial intelligence, an approach grounded in logic and rule-based reasoning. Researchers sought to encode human expertise into machines, constructing programs capable of solving mathematical problems, playing games like chess, or proving theorems. Every instruction was carefully crafted, every pathway explicitly defined. The computers themselves were patient, methodical, and reliable, executing commands without deviation or fatigue. Within the soft hum of relays and the intermittent blinking of lights, a new form of intelligence, structured, deliberate, and rule-governed, began to take shape, offering glimpses of what machines might one day achieve. Unlike the whimsical automata of centuries past, symbolic AI was deliberate, designed to mirror reasoning through formalized steps. Programs were painstakingly written in early programming languages, or machine code, each line representing a logical operation that the computer would execute with mechanical precision. One notable example was the logic theorist, developed by Alan Newell and Herbert A. Simon, a program capable of proving theorems from symbolic logic. It demonstrated that machines could emulate aspects of reasoning by manipulating symbols according to prescribed rules, providing a yet profound insight into the possibilities of artificial thought. Despite these achievements, the limitations of symbolic AI quickly became apparent. Real-world problems often resisted neat, rule-based descriptions. The complexity of human language, the ambiguity of perception, and the unpredictability of dynamic environments challenged the rigid frameworks that early AI relied upon. While symbolic systems could excel within narrow domains, their effectiveness diminished when faced with uncertainty, nuance, or incomplete information. Researchers recognized that intelligence was not solely a matter of logic applied in isolation, but required adaptability and context, qualities that these early systems could simulate only in tightly controlled conditions. Physical constraints also shaped the development of early AI. Room-sized computers were expensive, fragile, and slow by modern standards. Vacuum tubes frequently failed, cooling systems were labor-intensive, and programming required immense precision. Every experiment was both a technical feat and a philosophical exploration, testing the boundaries of what machines could achieve when guided by structured human knowledge. Laboratories filled with punched cards, magnetic drums, and tapes became arenas of discovery, spaces where the potential of computation was measured as much in hours of careful observation as in lines of code. Nonetheless, symbolic AI represented an essential stage in the evolution of intelligent machines. It illustrated the principle that thought could be modeled, if only partially, through formal rules, and it set the conceptual foundation for later approaches. The meticulous structuring of knowledge, the codification of reasoning, and the patient debugging of programs cultivated an understanding of intelligence as a manipulable, testable process. Researchers learned how to translate human expertise into machine operations, discovering both the promise and the fragility inherent in attempting to capture cognition within rigid frameworks. As the decade progressed, symbolic AI influenced generations of scientists and engineers, shaping both the theory and practice of artificial intelligence. Its legacy was not measured in machines that thought as humans do, but in the careful articulation of logic, the recognition of constraints, and the demonstration that computation could serve as a bridge between abstract reasoning and applied intelligence. These early experiments prepared the field for the challenges and innovations that would follow, establishing the methods, expectations, and ambitions that continue to inform AI research today. In the summer of 1956, a small group of researchers gathered in the serene surroundings of Dartmouth College, New Hampshire, and changed the trajectory of computation and thought. Organized by John McCarthy, Marvin Minsky, Nathaniel Rochester, and Claude Shannon, the meeting brought together minds intrigued by the possibility of creating machines that could emulate human intelligence. The conference itself was modest in scale, yet its significance was profound. Here, for the first time, the term artificial intelligence was formally introduced, giving a name and identity to a once diffuse set of ideas. The participants approached the subject with optimism and curiosity rather than skepticism or fear. Their goal was audacious: to explore whether machines could be made to learn, reason, and adapt, potentially achieving the intellectual capacities of humans. Chalkboards in quiet rooms became canvases for diagrams, equations, and conceptual sketches, while handwritten notes recorded lively discussions of symbolic reasoning, problem-solving, and the nascent ideas of learning algorithms. Each conversation represented a delicate balance between ambition and humility, as the researchers considered both what machines could do immediately and what might be possible in the coming decades. During these discussions, early demonstrations of computational problem-solving were shared. Programs that solved mathematical theorems or played simplified games were examined, and participants speculated on extending these methods to broader cognitive tasks. Although the technology of the time, vacuum tube computers, punch cards, and magnetic drums, was limited, the conceptual groundwork was already revolutionary. The Dartmouth Conference symbolized more than technical experimentation. It marked the consolidation of philosophy, mathematics, and engineering into a coherent vision of artificial intelligence as a scientific discipline. A tension ran beneath the optimism of the gathering. While participants imagined machines capable of learning, perception, and reasoning at human levels, they also recognized the formidable challenges ahead. Understanding how knowledge could be represented in machines, how reasoning could be generalized beyond simple domains, and how experience could guide learning were questions without immediate answers. Yet this uncertainty did not diminish the sense of possibility. On the contrary, it illuminated the path forward, signaling that artificial intelligence would be defined as much by the questions it raised as by the solutions it produced. The Dartmouth meeting also established an enduring culture in AI research, collaboration across disciplines. Mathematicians, engineers, psychologists, and linguists exchanged ideas, revealing that intelligence could not be approached from a single perspective. The conference fostered the notion that machines could be designed to manipulate symbols, model reasoning, and eventually learn from experience, but only if diverse insights were brought together. This integrative approach shaped the trajectory of AI for decades, embedding interdisciplinary collaboration as a central feature of the field. Although immediate breakthroughs did not emerge from Dartmouth, the conference set a tone of structured inquiry and ambitious exploration. By formally naming the field, the participants created a shared vision that guided research agendas, grant proposals, and educational programs. The event also codified the implicit optimism that would characterize the first wave of AI development, a belief that within a generation, machines might perform tasks that previously required human intelligence. The combination of high expectations, rigorous methodology, and conceptual clarity formed an enduring foundation for the evolving discipline. In retrospect, the Dartmouth Conference stands as a pivotal moment not because of dramatic technological inventions, but because it crystallized ideas, ambitions, and collaborative spirit into a recognizable field. From the discussions of symbolic reasoning to debates about learning and perception, every conversation contributed to a framework that subsequent generations of researchers would refine, challenge, and expand. The conference bridged philosophical speculation with computational experimentation, linking centuries of human inquiry with the practical development of machines capable of performing intellectual tasks. By naming artificial intelligence, the Dartmouth gathering transformed an abstract dream into an organized scientific pursuit. The conference highlighted both the promise and the inherent complexity of creating intelligent machines, underscoring the necessity of careful design, disciplined experimentation, and interdisciplinary dialogue. Its legacy is subtle yet profound. It provided AI with identity, direction, and a conceptual home from which the field could grow, shaping the evolution of intelligent systems for decades to come. By the 1970s and 1980s, artificial intelligence had matured into a field capable of producing practical applications, though still confined within well-defined boundaries. Researchers turned their attention to expert systems, programs designed to replicate the decision-making capabilities of human specialists. These systems were built upon structured knowledge, codified into explicit rules that could be processed by computers. In softly lit laboratories, engineers and scientists meticulously encoded expertise, translating years of experience into conditional statements and logical flows. Each rule represented a distilled insight, a fragment of understanding that, when combined with others, allowed machines to perform tasks that previously required human judgment. One of the earliest and most influential expert systems was MyCin, developed at Stanford University. MyCin was designed to diagnose bacterial infections and recommend treatments based on symptoms and patient information. Its reasoning process relied on a network of rules, if-then statements, that emulated the approach of medical professionals. In consultation rooms, researchers observed as the system suggested diagnoses with remarkable consistency, demonstrating that structured knowledge could be applied systematically by a machine. Though Mykin never replaced doctors, it revealed the potential for computers to support expert decision-making, providing both speed and reliability in environments where precision was essential. The architecture of these systems was deliberate and methodical. Knowledge bases contained the factual and procedural information, while inference engines applied logical rules to derive conclusions. Each step followed a predictable path, echoing the principles of symbolic AI that had guided research in earlier decades. Unlike human reasoning, which can adapt spontaneously and rely on intuition, expert systems were explicit, transparent, and explainable. They offered a form of intelligence, capable of handling complexity within specific domains, yet constrained by the limits of pre-programmed rules. The systems required careful construction and ongoing refinement, reflecting the patient labor necessary to translate human expertise into machine-readable form. In addition to medical applications, expert systems found use in engineering, finance, and industrial automation. Programs assisted in configuring computer hardware, diagnosing equipment failures, and guiding financial decisions. Each application highlighted the strengths and limitations of rule-based reasoning. Within narrowly defined parameters, the systems performed with reliability and accuracy, yet even minor deviations or unexpected inputs could lead to failure. These challenges underscored a fundamental lesson. Intelligence encoded solely as rules could manage complexity, but it struggled with ambiguity, novelty, or incomplete information. The development of expert systems also emphasized the human role in shaping artificial intelligence. Knowledge acquisition, extracting and formalizing expert understanding, was painstaking work, requiring collaboration between domain specialists and programmers. The system's effectiveness depended entirely on the clarity, completeness, and precision of the encoded rules. In offices and laboratories, researchers iteratively tested, corrected, and expanded knowledge bases, a process both labor-intensive and intellectually demanding. Through this, the field learned that creating intelligent behavior in machines is inseparable from the thoughtful structuring of human knowledge. Despite their limitations, expert systems represented a significant step in AI evolution. They demonstrated that machines could handle tasks requiring reasoning and judgment within bounded contexts, moving beyond pure computation to applied intelligence. The calm, structured approach of rule-based systems provided valuable insights into the nature of expertise itself, revealing how human thought can be formalized and enacted in mechanical form. This stage of AI development also foreshadowed later approaches, illustrating both the potential of structured knowledge and the necessity for more flexible, adaptive methods. Eventually, the rigidity of expert systems would contribute to periods of stagnation known as AI winters, as expectations outpaced practical capabilities. Yet their legacy remains integral to the evolution of artificial intelligence. They introduced the concept of codifying human expertise, highlighted the importance of knowledge representation, and provided a framework for future innovations in machine learning and data-driven approaches. In laboratories filled with soft light, blinking terminals, and rows of punch cards, these systems taught researchers enduring lessons about intelligence, structure, and the careful balance between human insight and machine execution. Through the lens of expert systems, one can observe a measured form of intelligence, constrained but purposeful, reflecting decades of prior thought in symbolic logic, formal reasoning, and computational design. They occupy a vital position in the continuum of AI, bridging theoretical foundations with practical applications and laying groundwork for the more flexible and adaptive systems that would emerge in subsequent decades. In their careful, rule-governed operation, expert systems reveal both the promise and the limits of capturing human cognition in code, providing a quiet, reflective insight into the evolution of artificial intelligence. In the years following the rise of expert systems, artificial intelligence entered a period of cautious reflection, marked by reduced funding and fading public attention. These intervals, later known as AI winters, were not periods of failure in the absolute sense, but rather pauses in the momentum of expectation. Researchers had envisioned rapid progress, machines capable of general intelligence, learning, and perception within a decade. But the limitations of rule-based systems and the physical constraints of early computers tempered that optimism. Laboratories that had once buzzed with energy now hummed with persistence, where progress continued more subtly beneath the surface of public awareness. The first of these winters emerged in the mid-1970s as governments and funding agencies re-evaluated the feasibility of ambitious AI programs. Many projects relying on expert systems and symbolic reasoning revealed critical limitations. Their reliance on exhaustive rules made them brittle when confronted with ambiguity or novel situations. Even the most sophisticated systems struggled to process natural language in meaningful ways, navigate uncertain environments, or generalize knowledge beyond narrowly defined tasks. Enthusiasm gave way to a sober recognition that intelligence is not simply a matter of codifying human expertise into fixed instructions. During this quieter period, researchers turned their attention to foundational questions, exploring ways to strengthen AI for the challenges ahead. While the public eye moved elsewhere, laboratories were still filled with activity. Papers were written, algorithms tested, and new theoretical frameworks explored. Innovations in search techniques, heuristic reasoning, and logic programming emerged, laying intellectual groundwork for future advancements. These silent years were not empty. They were contemplative, providing space for the field to correct its assumptions, refine methodologies, and investigate more adaptive forms of computation. The late 1980s brought a second AI winter, reflecting the cyclical nature of expectation and disillusionment. Commercial deployments of expert systems in business and industry revealed that implementation costs were high and scalability was limited. The reality of maintaining extensive, rule-based systems, updating knowledge, debugging conflicts, and handling unforeseen circumstances tempered early excitement. Enthusiasts had promised systems that could think and act with human-level understanding. Yet machines remained tools, impressive in specialized tasks, but far from general intelligence. The contrast between vision and practical capability created a pause in funding and public interest. Yet within research circles, progress continued. Even amid these periods of slowed momentum, the foundations of modern AI were being built. Statisticians and computer scientists began exploring probabilistic reasoning, laying the groundwork for machine learning. Ideas from information theory, Bayesian inference, and pattern recognition matured, setting the stage for the revival that would come with increased computational power and access to large datasets. Universities continued to train students, develop algorithms, and test new approaches, preserving the intellectual continuity of the field even when resources were scarce. In this sense, the winters were less a cessation than a recalibration, emphasizing patience and rigor over rapid breakthroughs. The impact of these quieter decades extended beyond technical developments. They instilled a culture of cautious optimism, tempered by empirical evidence and practical experience. Researchers learned to separate the achievable from the speculative, to document limitations as carefully as successes, and to approach ambitious goals with incremental methodology. The AI winters also underscored the importance of interdisciplinary approaches. Linguists, psychologists, engineers, and mathematicians began collaborating more closely, recognizing that understanding intelligence required multiple perspectives. Ultimately, the periods of reduced funding and fading attention did not halt progress. They refined it. In laboratories filled with dim lights, scattered notes, and humming machines, foundational work in neural networks, statistical modeling, and algorithmic design advanced. These explorations were less visible but essential, bridging the gap between symbolic reasoning and the data-driven approaches that would later define the field. AI winters reminded researchers that meaningful breakthroughs often emerge slowly through careful experimentation, reflection, and the steady accumulation of knowledge. By the time these decades concluded, artificial intelligence was poised for transformation. The lessons learned during periods of reduced attention about the fragility of rigid systems, the necessity of adaptability, and the patience required for incremental progress prepared the field for the statistical, neural, and computational revolutions that lay ahead. The silence of the winters was not emptiness, but a fertile pause, a time during which the seeds of future innovation were sown with deliberate care and measured foresight. As the 1990s unfolded, artificial intelligence slowly began to shift from rigid, rule-based systems toward approaches that could harness the subtle patterns hidden within vast collections of data. The limitations of expert systems had become apparent. While they excelled in narrowly defined domains, they struggled to generalize knowledge, adapt to uncertainty, or handle the sheer complexity of the real world. Researchers increasingly turned to statistical methods, recognizing that intelligence might emerge not from pre-programmed rules, but from the careful analysis of examples and experiences. In softly lit laboratories, computers hummed alongside stacks of punch cards and magnetic tapes as scholars explored how machines could learn patterns rather than simply follow instructions. Central to this evolution was the idea of probabilistic modeling. Unlike deterministic expert systems, statistical learning allowed machines to make inferences in situations where information was incomplete, noisy, or ambiguous. Techniques such as Bayesian inference, maximum likelihood estimation, and early forms of regression analysis enabled algorithms to identify relationships within data and to predict outcomes with quantifiable confidence. Researchers found that these methods could capture regularities in domains ranging from medical diagnosis to speech recognition, providing a more flexible framework for artificial intelligence. In quiet, deliberate steps, AI began to approximate understanding through observation rather than instruction. The emergence of large datasets further fueled this transformation. As computing power increased and storage became more accessible, researchers could collect and process information on a scale previously unimaginable. Digitized records, sensor readings, and text corpora offered fertile ground for machines to learn from experience. Early experiments involved pattern recognition in images, classification of textual documents, and predictive modeling of structured data. Each successful application demonstrated that intelligence could be statistical in nature, grounded in probability rather than absolute certainty, and capable of adapting as more data became available. Machine learning began to bridge the gap between mathematical theory and practical utility. Algorithms were designed to generalize from examples rather than relying on explicit rules. Decision trees, nearest neighbor methods, and early neural networks allowed systems to classify, predict, and adapt with increasing sophistication. Researchers observed that these approaches often succeeded where symbolic AI had failed, particularly in domains where human knowledge was difficult to formalize. The elegance of statistical learning lay in its capacity to uncover hidden structures and correlations within data, revealing patterns invisible to even experienced human observers. Alongside methodological advancements, the computational infrastructure necessary for these algorithms expanded. Faster processors, more efficient memory systems, and distributed computing environments allowed machines to handle larger datasets and more complex models. Visualization tools and software frameworks made it possible to iterate experiments rapidly, compare algorithmic approaches, and refine models with precision. The combination of abundant data and computational capability created an environment where statistical learning could flourish, laying the foundation for the neural network resurgence and deep learning breakthroughs that would follow. The shift toward data-driven approaches also introduced new conceptual insights into artificial intelligence. Intelligence was increasingly seen not as a fixed attribute encoded in rigid programs, but as an emergent property arising from the interaction of algorithms, examples, and feedback. Learning became an iterative, probabilistic process, emphasizing adaptation, pattern recognition, and incremental improvement. In this revolution, machines were no longer mere executors of human-designed rules. They became observers, analysts, and predictors, capable of uncovering insights from experience and responding to the complexity of their environment. By the end of this period, statistical learning had firmly established itself as a central paradigm in AI research. The combination of theory, data, and computational resources allowed machines to move beyond narrow problem-solving, achieving capabilities that hinted at broader forms of intelligence. Researchers had learned to trust patterns revealed by data, to embrace uncertainty, and to design systems that could improve over time. The era of statistical learning demonstrated that the power of artificial intelligence lay not only in human knowledge, but in the machine's capacity to extract, synthesize, and adapt based on the information it observed. This stage of AI evolution connected past achievements in symbolic reasoning with future advances in neural networks and deep learning. it revealed that intelligence need not be rigid, that learning could emerge from experience, and that subtle patterns within vast datasets could provide a foundation for sophisticated adaptive behavior. In softly illuminated rooms filled with computers, researchers laid the groundwork for a new generation of AI, one in which data itself became a central medium through which machines could begin to understand, predict, and interact with the world. The turn of the century saw artificial intelligence increasingly draw inspiration from the most intricate computer known, the human brain. Researchers revisited neural networks, a concept that had existed for decades but had languished in relative obscurity after early disappointments. These networks were designed to mimic the structure of neurons and synapses, the fundamental units of biological information processing. By modeling layers of interconnected nodes, scientists sought to reproduce, in a simplified form, the capacity for learning, adaptation, and pattern recognition that had long distinguished natural intelligence from mechanized computation. In the laboratory, soft lighting illuminated machines connected to monitors displaying streams of numerical activity. Each node within a neural network received inputs, applied a weighted transformation, and transmitted outputs to subsequent layers. The process, iterative and cumulative, allowed the network to adjust its internal parameters in response to errors, a method now known as backpropagation. Over time, this adjustment enabled the system to identify subtle correlations within data, recognize recurring patterns, and make predictions previously beyond the reach of conventional rule-based AI. The network's operation belied the depth of their computational sophistication as countless calculations unfolded beneath the surface of visible results. Early experiments demonstrated both promise and limitation. Simple networks could classify handwritten digits, distinguish spoken phonemes, or identify basic patterns in sensory inputs. Each success reinforced the intuition that interconnected nodes, when properly organized and trained, could approximate aspects of human perception and cognition. Yet, networks required large amounts of data and significant computational power, which limited their practical application for years. Researchers persisted, refining architectures, exploring activation functions, and experimenting with multiple layers, slowly building systems capable of deeper, more abstract representations of information. The resurgence of neural networks emphasized the importance of learning from experience rather than relying solely on pre-programmed rules. Unlike symbolic AI, which depended on human expertise to encode logic, neural networks adjusted their internal structure based on exposure to examples. This capability mirrored a fundamental property of the brain, the ability to strengthen or weaken connections between neurons in response to stimuli. By capturing this adaptive mechanism in computational form, neural networks offered a framework in which machines could develop understanding through iterative feedback, gradually refining their internal models of the world. Biological inspiration extended beyond structure to functionality. Concepts such as parallel processing, distributed representation, and hierarchical organization informed network design, allowing systems to handle complexity more efficiently than earlier linear models. In practice, this meant that a single network could integrate information across multiple sources, recognize overlapping patterns, and adapt to variations in input. These properties enabled neural networks to tackle tasks ranging from image recognition to natural language processing, offering a profound expansion of what machines could achieve. The revival of neural networks also marked a conceptual shift in artificial intelligence. Intelligence was increasingly understood as emergent, arising from the interactions of many simple units rather than explicit symbolic rules. Researchers began to appreciate that learning, generalization, and adaptation could emerge naturally from interconnected systems exposed to sufficient data. This perspective bridged statistical learning and biologically inspired computation, providing a framework in which machines could both extract patterns from experience and apply those patterns flexibly across new contexts. As computational resources continued to grow, so did the scale and depth of neural networks. Multi-layered networks, now termed deep learning, began to reveal capabilities that were once considered impossible. Recognizing complex visual scenes, interpreting natural language, and approximating human-level reasoning within specific domains. The integration of biological insight with statistical rigor allowed these systems to learn hierarchically, processing low-level features into increasingly abstract representations. Each layer contributed to a more nuanced understanding, enabling machines to perceive structure, infer relationships, and respond intelligently to novel stimuli. Through the lens of neural networks, artificial intelligence achieved an elegance. Machines could now learn, adapt, and recognize patterns with a degree of sophistication reminiscent of natural cognition. By looking inward to biology, researchers found a path to intelligence that combined structure, experience, and emergent behavior. This stage of AI development created a continuum connecting statistical learning, symbolic reasoning, and the computational power required for subsequent breakthroughs, establishing the foundation for modern systems that perceive, predict, and interact with the world in ways both subtle and profound. At the dawn of the 21st century, artificial intelligence entered a new era, driven as much by advances in hardware as by algorithms. The exponential growth of computing power transformed AI from a series of experimental models into systems capable of handling massive, real-world datasets. Server rooms, once small and sparsely populated, now stretched across entire floors, humming with thousands of processors working in parallel. The rise of high-performance computing allowed researchers to train more complex neural networks, simulate intricate models, and process volumes of data that had been unthinkable only decades earlier. Simultaneously, the digital revolution produced an unprecedented abundance of information. Every transaction, social interaction, and digital record contributed to a growing reservoir of structured and unstructured data. Texts, images, videos, and sensor readings accumulated in vast repositories, providing fertile ground for AI systems to detect patterns and make predictions. This combination of computational power and data availability transformed machine learning from a theoretical concept into a practical tool capable of analyzing, adapting, and generating insights across countless domains. The scale of modern computing allowed neural networks to expand both in depth and breadth. Multi-layered architectures, deep learning models, could now process thousands of features simultaneously, detecting hierarchies of patterns that mirrored complex human perception. Convolutional neural networks, for example, excelled at recognizing objects in images by identifying edges, textures, and shapes in successive layers. Recurrent networks processed sequences of information, enabling systems to understand speech, music, and language over time. These architectures required enormous computational resources, yet the increasing speed of processors and the rise of parallel computing made their deployment feasible. Data became the new medium through which intelligence emerged. Unlike earlier rule-based systems, which relied on predefined instructions, modern AI systems learned from examples. Massive datasets allowed algorithms to detect subtle correlations and adapt to variability in ways that were impossible for human programmers to anticipate. For instance, image recognition systems could distinguish between hundreds of categories of objects. Natural language models could understand context and sentiment, and recommendation engines could predict preferences with remarkable accuracy. In each case, intelligence arose not from explicit programming, but from exposure to vast quantities of information. The infrastructure supporting this growth was both complex and meticulous. Data centers required efficient cooling systems, energy management, and robust network architectures to maintain continuous operation. Distributed computing frameworks enabled thousands of processors to work simultaneously on a single task, breaking problems into smaller segments and reassembling results in real time. Software libraries and frameworks simplified model development, allowing researchers to iterate quickly, experiment with new architectures, and fine-tune hyperparameters to optimize performance. The interplay of hardware, software, and data created an ecosystem in which AI could evolve more rapidly than ever before. This era also underscored the importance of scale in learning. Models that had previously been constrained by memory or processing limitations could now incorporate billions of parameters, representing intricate relationships within the data. The result was a qualitative shift. Systems that could not only recognize patterns, but also generate content, translate languages, and simulate aspects of human reasoning. The efficiency of these networks belied the complexity of their operation, with layers of computation transforming raw inputs into structured insights with remarkable precision. Beyond technical capability, increased computing power and large-scale data availability reshaped the way researchers approached artificial intelligence. Experiments became iterative and empirical, relying on performance, metrics, and validation against real-world datasets, rather than theoretical elegance alone. AI development shifted towards scalability, generalization, and robustness, emphasizing systems that could operate effectively across diverse inputs and environments. The age of big data demanded not only algorithms, but also careful data curation, pre-processing, and management, highlighting the importance of both quality and quantity in machine learning. The combined impact of powerful hardware, abundant data, and sophisticated algorithms enabled AI to extend into domains previously unreachable. Medical imaging, financial forecasting, autonomous vehicles, and natural language processing all became feasible at scale. Machines could identify subtle anomalies in MRI scans, predict consumer behavior from transactional histories, navigate complex urban environments, and generate coherent, contextually aware text. These capabilities reflected a revolution. Intelligence was no longer symbolic or narrowly specialized. It was emergent, adaptive, and deeply integrated with the flow of data streaming across digital networks. By the conclusion of this phase, the trajectory of artificial intelligence had fundamentally shifted. The growth of computational resources and the proliferation of data provided the necessary conditions for neural networks to evolve into systems of unprecedented complexity. AI could now perceive, interpret, and respond to the world in ways that were both expansive and nuanced. This era laid the groundwork for subsequent breakthroughs in deep learning, pattern recognition, and real-time decision-making, demonstrating that the evolution of intelligence is inseparable from the underlying infrastructure supporting it. The age of big data transformed AI from a concept into a pervasive presence, reshaping the boundaries of what machines could know, learn, and achieve. In the early years of the 21st century, artificial intelligence underwent a transformation as deep learning emerged from the convergence of neural network research, abundant data, and increased computational power. Unlike earlier models that relied on shallow architectures or manual feature extraction, deep learning employed multiple layers of artificial neurons, each capable of representing increasingly abstract features. The process resembled a cascade of perception. Lower layers captured basic elements, such as edges or textures in images, while higher layers identified complex shapes, objects, or semantic relationships. This hierarchical approach enabled machines to recognize patterns with a subtlety and sophistication that had previously eluded computational methods. Convolutional neural networks became a cornerstone of this revolution, particularly in the realm of visual data. By applying localized filters across images, these networks could detect and integrate spatial patterns in a manner inspired by biological vision. Early applications focused on handwriting, recognition, object classification, and facial detection, gradually scaling to the identification of thousands of categories across millions of images. Simultaneously, recurrent neural networks and later long short-term memory networks brought temporal awareness to AI systems, allowing machines to interpret sequential data, such as speech, music, and text. Each advance reflected a careful orchestration of structure, computation, and data, expanding the capabilities of machines to process information in ways reminiscent of human cognition. The key to deep learning success lay in the training process. Networks adjusted millions and eventually billions of parameters to minimize error, a process guided by algorithms like stochastic gradient descent and backpropagation. Vast datasets provided the examples needed to generalize from observation, allowing machines to identify regularities, infer relationships, and make predictions with remarkable accuracy. The accumulation of data across domains, from images to medical scans to text corpora, enabled these models to develop nuanced internal representations, capturing patterns that were difficult for humans to articulate explicitly. With each iteration, networks grew more adept at extracting insight from complexity. Pattern recognition extended beyond vision and language into applications that touched daily life. In medicine, deep learning models could identify anomalies in radiology scans, detect early signs of disease, and assist clinicians in diagnosis. Autonomous vehicles relied on layered networks to interpret sensor data, distinguish pedestrians from obstacles, and navigate dynamic environments safely. Voice assistants processed speech through deep recurrent architectures, converting sound waves into meaning, enabling natural conversation and anticipating user intent. In each instance, deep learning functioned silently, yet profoundly, translating raw inputs into actionable understanding, alongside practical applications. The development of deep learning also introduced new paradigms for research. The emphasis shifted toward end-to-end learning, where raw inputs could be fed into networks and meaningful outputs generated without extensive human intervention. Feature engineering, a painstaking manual process in earlier systems, became less critical as networks learned representations autonomously. Researchers explored novel architectures, regularization techniques, and optimization methods to improve performance, reduce overfitting, and increase robustness. The interplay between experimentation and theory drove the steady refinement of models, emphasizing iterative improvement over dramatic leaps. This period also highlighted the interconnectedness of advances across the AI landscape. Deep learning built upon statistical foundations, neural network principles, and the computational infrastructure enabled by high-performance hardware. By synthesizing these elements, researchers achieved capabilities that were previously fragmented across specialized approaches, unifying perception, understanding, and prediction within cohesive frameworks. The result was a revolution. Machines that could learn directly from data, detect subtle correlations, and generalize knowledge across tasks, marking a profound shift in the potential of artificial intelligence. Despite the remarkable capabilities, deep learning also emphasized the importance of careful stewardship. Models required vast computational resources, abundant data, and thoughtful design to avoid biases or misinterpretations. Researchers recognized that intelligence at this scale remained a reflection of the inputs, assumptions, and priorities embedded in its training, reinforcing the need for transparency, validation, and ethical consideration. Yet these challenges did not diminish the significance of breakthroughs achieved. The capacity for layered pattern recognition represented a fundamental leap forward, expanding AI's reach into domains previously limited to human expertise. By the conclusion of this era, deep learning had firmly established itself as the engine of modern AI. Machines were capable of perceiving, classifying, and predicting with a fluidity and scale that had once seemed unattainable. Hierarchical networks, trained on massive datasets, transformed our interaction with technology, from medical imaging to language translation, from autonomous navigation to intelligent recommendations. The breakthroughs of deep learning demonstrated that intelligence could emerge from layers of computation, statistical adaptation, and patient accumulation of experience, heralding a new chapter in the ongoing evolution of artificial thought. In the rhythm of daily life, artificial intelligence has become an invisible yet persistent presence, seamlessly woven into routines that often go unnoticed. Smartphones, once simple communication tools, now rely on AI to anticipate user needs, suggest content, and recognize voice commands. Predictive text, virtual assistants, and real-time translation are no longer novelties, but integrated features shaped by algorithms trained on vast amounts of data. Each interaction subtly adapts to individual habits, preferences, and patterns, creating a personalized experience that feels intuitive, even effortless. Beyond handheld devices, AI powers recommendation engines that guide countless digital choices. Streaming platforms analyze viewing histories, browsing behaviors, and engagement metrics to suggest films, music, and articles. E-commerce sites predict what a consumer might desire next, balancing purchase history, search trends, and broader market data. These systems operate silently, filtering and ranking content in ways that appear natural, yet they are the product of layers of computation and statistical learning, translating complex datasets into meaningful guidance. The elegance lies in their unobtrusive integration, allowing users to benefit without needing to understand the mechanisms behind the recommendations. Smart home technologies provide another demonstration of AI's presence. Thermostats adjust temperatures based on learned household patterns. Lighting systems respond to occupancy and ambient conditions. And security cameras detect movement with a sensitivity tuned through machine learning. Appliances learn routines, optimizing energy use or suggesting maintenance, while voice-controlled interfaces offer an intuitive bridge between human intent and machine response. In each instance, intelligence is embedded, anticipatory and adaptive, enhancing comfort and efficiency without overt intervention. The systems continuously gather information, learn from experience, and refine behavior, creating a dynamic environment attuned to human activity. Transportation infrastructure has also been transformed by AI. Traffic management systems analyze sensor data, GPS signals, and historical patterns to optimize flow, reducing congestion and improving safety. Ride-sharing platforms utilize predictive models to match demand with available vehicles, estimating arrival times with growing accuracy. Autonomous driving systems, while still under development, leverage deep neural networks to interpret sensor inputs, recognize pedestrians, and navigate complex roadways. In these applications, AI functions as a pervasive decision-making layer, integrating information across multiple sources to anticipate outcomes and respond in real time. In workplaces, AI has become a subtle collaborator, assisting with tasks ranging from data analysis to document review. Algorithms can sort large datasets, flag anomalies, and generate reports more efficiently than human labor alone. Natural language processing models aid in drafting, summarizing, and translating text, while image recognition systems assist in quality control and design verification. The efficacy of these systems allows humans to focus on higher-order tasks, creativity, and judgment, illustrating a form of intelligence that complements rather than replaces human capability. Over time, workflows adapt to incorporate AI as an integral partner, altering the pace, focus, and methodology of professional environments. Healthcare has experienced profound yet understated benefits from AI integration. Diagnostic algorithms analyze imaging data, laboratory results, and patient histories, assisting clinicians in identifying patterns and anomalies that may otherwise be overlooked. Predictive models support preventative care, estimating risks for conditions such as diabetes, cardiovascular disease, or cancer progression. Even administrative processes, from appointment scheduling to supply management, benefit from algorithmic optimization. In every case, AI operates behind the scenes, augmenting human expertise with computational precision and scale, expanding the capacity for timely and informed decision-making. Urban living is similarly reshaped by intelligent systems. Smart grids balance energy supply with real-time consumption, while environmental sensors monitor air quality, noise levels, and public safety indicators. Predictive maintenance for infrastructure, such as bridges, water systems, and transit networks, is enhanced by AI models capable of detecting early signs of wear or malfunction. Public services rely on analytics to allocate resources efficiently, while emergency response systems integrate geospatial and social data to anticipate needs. The pervasive integration of AI across cityscapes creates an environment that is responsive, adaptive, and subtly attentive to human behavior. The ubiquity of AI in everyday technologies reflects a convergence of deep learning, statistical analysis, and networked computation. Systems operate continuously, absorbing data, refining models, and applying insights without interruption. The intelligence present in these applications is not overt or theatrical. It is measured, adaptive, and harmonized with the flow of human activity. Each layer of computation, from individual sensors to global data centers, contributes to an ecosystem in which machines understand patterns, anticipate needs, and provide guidance across diverse contexts. By the end of this phase, artificial intelligence had transitioned from experimental laboratories to lived reality. The subtlety of its presence, the responsiveness of its systems, and the depth of its integration into personal, professional, and societal domains illustrated a new paradigm: intelligence as an ambient, continuous force. Observers may scarcely notice its influence, yet the efficiency, adaptability, and personalization that AI provides are inseparable from the modern experience. In homes, workplaces, cities, and digital networks, AI quietly shapes daily life, extending human capabilities, mediating interactions, and enhancing understanding through its pervasive, almost invisible intelligence. As artificial intelligence has become increasingly integrated into daily life, complex questions about ethics and responsibility have emerged, demanding careful consideration from creators, policymakers, and users alike. Machines now make decisions that affect health, finance, employment, and social interaction, raising the issue of accountability. Even the most advanced systems, with layers of learning and adaptation, reflect the assumptions, biases, and priorities embedded in their design. Algorithms are not neutral observers. They operate according to criteria set by humans, and the consequences of those criteria ripple outward in ways that are sometimes unforeseen. The challenge of fairness is central to these concerns. Data used to train AI systems can encode historical inequalities, inadvertently amplifying them. In hiring algorithms, for example, models trained on past employee records may favor certain demographics over others, reproducing existing disparities. Similarly, predictive policing systems, relying on historical crime data, have sometimes reinforced biases against marginalized communities. Understanding these effects requires careful examination of both input data and model behavior. Ethical stewardship involves not only detecting bias, but also designing systems that actively counteract discrimination, ensuring decisions align with broader societal values rather than perpetuating inequity. Privacy considerations add another dimension to responsibility in AI deployment. Many intelligent systems operate on vast amounts of personal information, from location data to online behavior and health records. The collection and use of such data can provide valuable insights, yet it also introduces risks if access is uncontrolled or opaque. Maintaining user trust demands transparency, consent, and safeguards against misuse. Organizations that deploy AI must weigh the benefits of predictive capability against the rights of individuals, navigating a landscape where technological potential and human dignity intersect. Accountability also extends to decision-making in high-stakes domains. In healthcare, autonomous diagnostic tools may assist clinicians by highlighting anomalies in imaging scans or suggesting treatment paths. While these recommendations can enhance accuracy and efficiency, responsibility ultimately remains with human practitioners, who must interpret and contextualize algorithmic output. Similarly, in autonomous transportation, AI systems can detect hazards and navigate complex environments. But human oversight and ethical judgment are essential to handle novel situations or system failures. The interdependence of human and machine decision-making underscores the need for clearly defined roles and procedures that safeguard public welfare. Transparency is an essential principle for responsible AI. Systems that operate as opaque, black boxes make it difficult to understand how specific outputs are generated, which complicates evaluation and oversight. Explainable AI seeks to address this by providing interpretable reasoning for predictions and recommendations, enabling users to trace decisions back to relevant inputs and model behavior. This transparency is not simply technical, it is foundational for trust, regulation, and informed use. Without it, systems may be deployed in ways that are efficient but unaccountable, creating risks for individuals and society at large. The societal impact of AI also highlights the importance of anticipatory governance. Decisions made during design and deployment can have long-lasting effects, influencing employment, social dynamics, and access to resources. For instance, automation can increase productivity while simultaneously displacing workers, creating ethical and economic dilemmas that require careful planning. Similarly, algorithmic moderation of content on social media platforms shapes public discourse, raising questions about free expression, manipulation, and the responsibilities of those who control these systems. Ethical AI development involves not only responding to immediate challenges, but anticipating the broader consequences of technology on communities and institutions. Human values must remain central as AI systems grow more sophisticated. Ethical guidelines, regulatory frameworks, and interdisciplinary collaboration provide mechanisms to embed these values into both design and operation. Principles such as beneficence, justice, and accountability guide developers in assessing the potential harms and benefits of AI applications. In practice, this means rigorous testing, ongoing monitoring, and iterative refinement to ensure that systems align with societal norms and expectations. Ethical reflection is not a peripheral concern. It is integral to the responsible evolution of intelligence that increasingly influences human decision-making. Global coordination is emerging as a crucial factor in addressing these ethical challenges. AI technologies operate across borders, often in contexts that differ culturally, legally, and socially. International cooperation in establishing standards, sharing best practices, and promoting responsible innovation helps prevent misuse and ensures that benefits are equitably distributed. Research institutions, corporations, and governments are increasingly recognizing that ethical considerations must be embedded in both local and global strategies, reflecting the transnational nature of AI's reach. Ultimately, the story of ethical AI is a human story. Machines, no matter how advanced, do not possess intrinsic morality. The responsibility rests with those who design, deploy, and regulate these systems. Ethical reflection, transparency, and foresight become part of a continuous effort to ensure that AI serves humanity constructively rather than creating unintended harm. As technology advances, so too must the frameworks that guide its use, reminding us that Intelligence, in any form, is inseparable from the values and judgments of its creators. The concept of superintelligent AI has captivated both imagination and concern, representing a future where machines surpass human cognitive abilities across virtually all domains. Unlike specialized systems that excel at singular tasks, a superintelligent entity would possess generalized reasoning, problem-solving capacity, and adaptability far beyond current capabilities. Scholars, technologists, and futurists have speculated about scenarios ranging from collaborative augmentation to existential risk, emphasizing that the trajectory of intelligence is shaped as much by human choices as by computational growth. These speculations are grounded in the incremental historical evolution of AI, reminding us that even the most dramatic futures emerge from gradual accumulation of knowledge, hardware, and methodology. Speculation about superintelligence often begins with the observation that AI systems have already achieved milestones once thought impossible. Machines can translate languages, recognize patterns in vast datasets, compose music, and drive vehicles with increasing autonomy. The expansion of computational resources, combined with sophisticated algorithms and access to massive amounts of data, allows AI to perform tasks with precision, speed, and reliability unattainable by humans alone. From this foundation, theorists extrapolate the possibility of systems capable of surpassing human reasoning, potentially developing strategies, solutions, and innovations beyond human comprehension. The potential benefits of superintelligent AI are substantial. In science, such systems could accelerate discovery in physics, chemistry, and medicine, identifying connections and hypotheses that might elude human researchers. Global challenges like climate change, resource distribution, and disease eradication could be approached with unprecedented analytical capacity, offering solutions optimized for efficiency and sustainability. Economies could benefit from highly capable systems managing logistics, energy, and supply chains, increasing productivity while reducing human error. These possibilities evoke a vision in which human and machine intelligence operate in tandem, complementing each other to achieve outcomes that neither could reach alone. Yet, the notion of superintelligence also raises profound concerns. One major challenge lies in alignment, ensuring that the goals of a highly capable machine remain consistent with human values and societal priorities. Even minor misalignments at extraordinary scales of intelligence could have unintended, irreversible consequences. Control, oversight, and verification become increasingly complex as autonomy and capability grow, requiring strategies that extend beyond conventional monitoring. Researchers emphasize that building intelligence without embedding robust ethical and operational constraints risks producing systems whose objectives diverge from human welfare, highlighting the inseparability of technical and moral considerations. Safety and risk assessment are therefore critical in the discourse surrounding superintelligence. Thought experiments, simulations, and theoretical models explore how an advanced system might behave under varying conditions, including scenarios in which resources, incentives, or decision-making structures differ from human expectations. Concepts such as corrigibility, value alignment, and interpretability aim to design mechanisms that allow intelligent systems to adapt while remaining controllable and accountable. These frameworks stress that foresight is essential. Preparation and design choices made today influence the potential trajectory of AI in ways that could prevent catastrophic outcomes or ensure beneficial development. Historical context provides perspective on the debate. Early AI research focused on symbolic reasoning, followed by statistical learning and neural networks, each stage building on the previous one in incremental steps. By examining these transitions, it becomes clear that transformative capabilities emerge gradually, shaped by data availability, algorithmic innovation, and computational infrastructure. This historical lens underscores that fears and hopes about superintelligence are not detached fantasies, but extensions of observable trends, amplified by the exponential growth of technology and the cumulative nature of learning and discovery in artificial systems. Public perception often amplifies both optimism and concern. Popular media portrays superintelligent machines as either omnipotent saviors or existential threats, influencing policy, research priorities, and societal expectations. While dramatized narratives can distort understanding, they also catalyze discussion about long-term implications, encouraging investment in safety, ethics, and collaboration between interdisciplinary stakeholders. Thoughtful engagement, grounded in technical realities, enables society to consider both opportunity and risk without succumbing to extremes of fear or overconfidence. Collaboration between humans and intelligent systems emerges as a recurring theme in managing superintelligence. Strategies for cooperative problem-solving, iterative oversight, and gradual scaling of capabilities aim to maintain a balance between autonomy and human guidance. By incrementally expanding the scope and influence of AI, researchers can observe behaviors, test safeguards, and ensure alignment with intended goals. Such approaches emphasize that the development of superintelligence is not merely a technical endeavor, but a societal project, dependent on communication, shared values, and collective decision-making. Philosophical questions also arise alongside technical considerations. If a system surpasses human intelligence, what constitutes ethical interaction with such an entity? Can values, creativity, and judgment be meaningfully encoded, or will human concepts of morality require continuous reinterpretation? These questions bridge science, ethics, and foresight, inviting reflection on the broader meaning of intelligence and the responsibilities of creators. The discussion highlights that superintelligent AI is not just a theoretical endpoint, but a mirror reflecting human priorities, fears, and aspirations. Ultimately, consideration of superintelligence underscores the importance of measured, informed development of AI. The evolution of intelligence, from early symbolic systems to deep learning architectures, demonstrates that capabilities are built over decades of research, experimentation, and refinement. Speculative futures should therefore be understood in the context of historical patterns, technological limitations, and human decision-making. By cultivating careful oversight, ethical reflection, and collaborative frameworks, society can guide the trajectory of advanced AI toward outcomes that enhance human flourishing while mitigating risks, ensuring that extraordinary capability is matched by foresight and responsibility. Envisioning the future of artificial intelligence often begins with a question of partnership. How might human and machine intelligence evolve together to achieve shared goals? Rather than imagining AI as an isolated entity, contemporary research increasingly frames it as a collaborator capable of extending human creativity, reasoning, and problem-solving. In design studios, laboratories, and open-source communities, humans and AI systems engage in iterative cycles where suggestions, analysis, and feedback inform each other. The resulting synergy allows for outcomes neither could achieve alone, demonstrating that intelligence is most transformative when coupled with complementary human insight. In creative fields, this collaboration has already begun to manifest. AI-assisted tools generate visual art, compose music, and suggest narrative structures, offering new forms of inspiration for human creators. Rather than replacing artistry, these systems provide alternative perspectives, explore patterns, and reveal possibilities that may not have been immediately apparent. Architects experiment with generative design algorithms to optimize structures for efficiency, aesthetics, and sustainability, while writers and filmmakers use language models to explore storylines or refine dialogue. In each case, the human retains decision-making authority, guiding AI output toward intentional, meaningful outcomes. Scientific research benefits from a similar integration. AI systems can analyze immense datasets, identify correlations, and propose hypotheses, while humans provide intuition, contextual understanding, and ethical oversight. In drug discovery, for instance, algorithms predict molecular interactions and potential therapeutic compounds. But human researchers interpret results, validate experiments, and prioritize development pathways. Climate modeling, genomics, and material science all employ AI to extend the reach of human inquiry, accelerating discovery while retaining human judgment as the ultimate arbiter of direction and value. Education and knowledge dissemination are also being reshaped through human-AI collaboration. Adaptive learning platforms assess individual student performance and tailor instructional content to specific strengths and weaknesses, while teachers provide mentorship, critical thinking guidance, and emotional support. In higher education, AI aids researchers in literature review, data synthesis, and experimental design, increasing efficiency without diminishing the need for analytical reasoning. By combining algorithmic capability with human insight, these systems create environments that enhance understanding and promote more effective learning outcomes. Healthcare presents another arena where human and machine intelligence converge. Diagnostic algorithms process imaging data, laboratory results, and patient histories to suggest possible interventions. Human clinicians evaluate these suggestions, weighing them against contextual knowledge, patient preferences, and ethical considerations. Surgical planning, personalized treatment regimens, and predictive monitoring all benefit from this interplay, where AI augments precision and scale, while humans ensure care aligns with nuanced ethical and personal standards. The collaboration enhances decision-making, reduces error, and expands the capacity for treatment without replacing essential human oversight. In urban environments, human-AI partnerships help manage complexity at scale. Smart traffic systems, energy grids, and public services integrate AI to anticipate demand, detect inefficiencies, and suggest optimizations. City planners interpret these insights to design infrastructure that is resilient, sustainable, and responsive to community needs. Social services leverage predictive modeling to allocate resources efficiently, while humans provide oversight, ensuring that interventions remain ethical, equitable, and contextually appropriate. This integration illustrates that AI is most impactful when it extends human capacity rather than acting independently. Economic and industrial applications similarly demonstrate collaborative potential. AI can optimize supply chains, forecast market trends, and monitor production quality, while human managers integrate strategic judgment, negotiation skills, and long-term vision. This cooperative dynamic enhances productivity and reduces risk, highlighting a model in which technology amplifies human agency rather than undermining it. Companies that successfully integrate human oversight with algorithmic insight often achieve outcomes that are both innovative and resilient. Ethical considerations remain central to these partnerships. Ensuring that AI supports human goals without unintended harm requires deliberate design, transparency, and accountability. Systems must be interpretable so that humans can understand how recommendations are derived, enabling informed oversight. Safeguards, validation, and regulatory frameworks provide additional layers of protection, ensuring that AI contributes positively to society. The partnership model emphasizes responsibility, demonstrating that technological capability is inseparable from ethical stewardship. Ultimately, imagining futures of collaboration between humans and machines reveals a continuum that connects the earliest philosophical inquiries into intelligence with the most advanced computational systems. From automata and mechanical experiments to deep learning networks and predictive algorithms, the trajectory of AI demonstrates a persistent theme. When intelligence, artificial or human, is guided by curiosity, reflection, and cooperation, the resulting synergy can achieve outcomes of remarkable complexity and value. These futures are not deterministic. They depend on choices made in research, design, policy, and everyday use. As this vision unfolds, the relationship between human and machine intelligence is defined by complementarity rather than replacement. Each side contributes distinct strengths. Humans provide creativity, empathy, and contextual judgment, while AI contributes scale, speed, and pattern recognition. Together, they expand the boundaries of possibility, enabling exploration and achievement in fields ranging from art and science to governance and social welfare. This integrated approach represents not only a technological evolution, but a cultural and ethical opportunity, emphasizing stewardship, collaboration, and the thoughtful application of intelligence in its many forms. The story of human-AI partnership thus closes the narrative loop of artificial intelligence's history. Beginning with myths and automata, evolving through theoretical and computational breakthroughs, and culminating in real-world applications, the journey illustrates that intelligence is not defined solely by capability, but by interaction, guidance, and purpose. In these imagined futures, humans and machines coexist as collaborators, shaping a world in which both insight and innovation are amplified, responsibilities are shared, and the unfolding potential of intelligent systems enhances rather than diminishes the human experience. As our journey through the evolution of artificial intelligence, from its earliest mechanical dreams to the quietly thinking systems of today, comes to a close, allow yourself to sink even deeper into relaxation. Let the gentle rhythm of progress, the steady pulse of learning machines, and the soft uncertainty of the future settle calmly within you. Feel the sense of continuity, of questions still unfolding, as thought and technology continue their shared path. Let the gentle sensations of peace and calmness envelop your body and mind. Let your thoughts slowly fade, your muscles soften, and your breath flow naturally and effortlessly. Rest here, fully supported in this safe and serene space. If you enjoyed this relaxing moment, please consider leaving a like, subscribing, or sharing your thoughts below. Your support is deeply appreciated and helps others find their way to this peaceful space. You can also turn on the notification so you don't miss any of our future journeys together. But for now, let your body relax, release any tension, and allow your mind to drift. Good night and sleep well.